The Chatelier's principle. So we're back into our fantasy land here. Not Clash of Clans. We're going to go, more literature here. I think we had Narnia on the left and Middle-earth on the right. Did you know that you can actually get the weather in Narnia on your iPhone? Pardon me? No, it isn't, actually. The time I looked at it, it wasn't. Because they did kill the Wicked Witch, and winter was ended, so I think that it's okay now. Yeah. So here we are again, Narnia and Middle-earth. We use this as an analogy to describe dynamic equilibrium and how even though you end up with constant concentrations on each side of the border, you do have migration back and forth. People are still immigrating from one to the other. So now we're going to say, well, what happens if the equilibrium is disturbed over here? The book says, what if there's a baby boom? Whole bunch of babies born over here. Population goes up. Maybe there's something in the water. So bunch more people over here. What's going to happen to the rates of migration back and forth? People are going to move away because it's getting too crowded. So the population is going to shift to Narnia to equilibrate again. And this is what Le Chatelier's principle says. When a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. So in this example, the disturbance was a population increase here. The only thing that can happen here is that people can move over here. That will decrease this population. It's fighting against change. I don't like change personally myself, and so this just resonates with me. The equilibrium has everything sorted out, and then you go and mess with it. And it says, no, we're going to try to get as close to where we were as possible. So if you increase something, it's going to move to decrease it. Le Chatelier's principle. So there are different ways that we can mess with an equilibrium. We can change the concentration. Here we have N2O4 and NO2. If we add product, this is like adding people to Middle-earth, this will cause the reaction equilibrium to shift to the left, and the population, the concentration of N2O4 will increase, and this will decrease from its elevated place when we add it. Another way to think about this is before the addition, the reaction quotient is equal to the equilibrium constant. When we add more product, remember remember what Q was? It's the same as the expression for K, but it's not equilibrium concentrations. So it's NO2 squared over N2O4. So the expression is the same, it's just what kind of concentrations are we putting in here. So if we're increasing this, that's going to increase the value of Q. Q is going to be larger than K. The system is going to move to reduce Q back down to K, and it will do that by shifting to the left. Here's in pictures. Pictures can be real helpful. So here we have a depiction of equilibrium, and we throw a bunch more of these NO2 in here. The equilibrium is disturbed. The reverse reaction is going to happen at an increased rate because there are more of those reactant molecules. And the result will be an increase in N2O4 and a relative decrease from what happened right after the addition. Now, the equilibrium constant is not changing, is it? It's just the concentrations are shifting around to continue obeying that constant. If we add reactant, it's going to cause it to shift the other way. So adding this, we want to get rid of some of it. We want to correct the wrong. And so the reaction will shift to the right. You can think of it this way. At equilibrium, Q equals K. After you add reactant, Q becomes less than K. And so the reaction needs to go forward to bring Q back up to K. Here's graphs. I'm just throwing all these out here because hopefully one of them will just like, yeah, that made a lot of sense. So here we have our equilibrium concentrations, and we're adding some NO2. So this one goes up, and as this reacts then, the N2O4 increases, and they're gradually going to come and reestablish a new equilibrium. What I like about this graph is that it illustrates the fact that the concentrations have changed afterwards, right? They've both gone up. But instead of this one going up a lot and this one staying the same, they've both gone up, and so their relationship between the concentrations is still equal to the equilibrium constant. Here we're adding N2O4, so this one goes way up. As that reacts, it gradually comes down. This goes up, and again, we get a new equilibrium established where these new equilibrium concentrations are different than what was there before. Any questions? It's a concept that you just have to get clear in your head. Then you can reason out all kinds of stuff without having to memorize junk. Yes?
So the numerical equilibrium changes as well, right? It's still the same for each one.
The equilibrium constant is still the same. The equilibrium constant doesn't change. These concentrations, at this point right here, K is not equal to Q, or we should say Q is not equal to K, because we've changed this concentration. Because for this guy, N2O4 was the reactant, right? Anybody? Okay, I'll go look myself. Oh, it's at the top. Duh. Yeah, this is the reactant. So Q equals the products. I just wrote this, but I can't remember. Over N2O4. When we add a bunch of this, when we increase this number, Q gets smaller. Remember, the reaction quotient tells us which direction the reaction is going to go to get to equilibrium. So it's going to go in a direction that Q gets larger. We added stuff down here that made Q small, and so it's going to move in a direction that reduces N2O4 and increases NO2. That's the forward direction. Okay? So summary, I don't recommend memorizing this, and just even typing it out, it's like, wow, it's just, sometimes when you put things down in writing like that, it's like really confusing looking. If you add reactant, it'll shift to the product. If you add product, it'll shift to the reactant. If you take reactant away, it's going to say, hey, we need to make more of that, and it'll shift to the reactant. It's trying to undo what you did to it, like a stubborn child. Okay, so here's a reaction. What's the effect of adding more bromine? So if we add bromine, what's it going to do to the equilibrium? Shift left or right? It's going to shift to the left. We add bromine, it's going to move in a direction to reduce the concentration of bromine. What if we add BrNO? It'll go to the right. Okay? Look, no numbers, just arrows. What about changing the volume or the pressure? Well, remember from Pivner that the pressure and the volume of a gas are inversely proportional. If you decrease the volume of a gas, you increase its pressure. If you increase the volume, you decrease the pressure. So if we change the volume of a reaction mixture that's at equilibrium, the pressure will change. And the system shifts in a direction to minimize that pressure change. This is for reactions that have products in the gas state. Pressure change does not affect liquids and solids or aqueous things. So let's look at this reaction. We've got nitrogen and hydrogen in a piston, in a cylinder with a piston, and it's in equilibrium with ammonia. What happens to the volume if we push down on the piston? The volume decreases. And what happens to the pressure? It increases. So the reaction wants to decrease the pressure. What can it do? Well, let's look. Here we've got 1 mole of gas and 3 moles of gas. Total of 4 moles of gases. And on the right side, we have 2 moles of gases. PV equals nRT. So we made the volume smaller, the pressure went up. How can we make that pressure come back down? We can change N. So if the reaction goes this way, we make more gas. That's going to increase the pressure. If we go this way towards products, we're going to have fewer moles of gas. The pressure of a gas depends on the number of moles, not on what the moles are. Remember, what the particle of gas is doesn't matter because there's so much space between the particles. So the pressure can be lowered by decreasing the moles of gas. And that would be a shift to the right. Does that make sense? So there'll be questions like this. And if they're talking about volume changes, put it into pressure. What's that doing to the gas? Increasing, decreasing the pressure. How can the reaction shift to change the number of moles of gas so that it can compensate for that pressure? What would happen if you added helium gas to this mixture? The total pressure goes up.
Of the partial pressure. Well, then nothing.
But if the partial pressures aren't going to change.
Oh, so, okay.
Remember, this equilibrium is governed by an equilibrium constant relative to pressure, Kp. And so it's not going to matter.
So in theory, if you put enough pressure, will it all turn into gas?
Yeah, you can use pressure to definitely control the equilibrium of the reaction. So here's the picture version. So we push down on this, causing a smaller volume, increased pressure. It will shift to the right where there are fewer moles of gas. If we pull up on this, we increase the volume, decrease the pressure. Now the reaction equilibrium shifts to the left, making more moles of gas to compensate. So decreasing the volume causes a shift to the direction that has fewer particles of gas. Increasing goes to greater. If you have a reaction with an equal number of moles of gas on both sides, changing the pressure has no effect. There's no reason for the equilibrium to shift if it can't do anything about the pressure. And if you add an inert gas at a fixed volume, that also has no effect. It does affect the total pressure, but it affects the partial pressures of those gases are going to be the same. It's not the total pressure, it's the partial pressures. It'll have no effect on the equilibrium. You throw an inert gas like helium in there, no effect. So let's look at this one. SO2 plus O2 going to SO3. What is the effect of decreasing the volume? Well, decreasing the volume increases the pressure, so it wants to go to fewer moles of gas, right? So 3 on the left, 2 on the right, it's going to go to the right. What if we increase the volume? Let's go to the left. And so literally, when I answer a question like that, this is what I think. decreasing the volume. Decreasing the volume increases the pressure. It's fighting back. It wants to reduce the number of moles of gas, find the side with fewer moles. That's where it goes. That's what goes through my head when I answer a question like that. I do not rattle that off. I don't know. There's no place in my head to just remember that instantly. What about temperature? If the temperature of a system changes, the system will shift to minimize the temperature change. So we can think of heat as a reactant or a product. And throughout this discussion, we're going to assume that when we have heat being added or removed, we're going to have constant pressure. We're not going to make things complicated. So an exothermic reaction, we can think of heat as a product. And an endothermic reaction, we put heat in, and it's a reactant. So exo, heat leaves, exits. Endo, heat goes in. So then, if we change the temperature of an exothermic reaction, here we're going to raise the temperature. Raising the temperature is like adding heat to the system, right? So if we're adding heat for an exothermic reaction, heat is a product. You add more product, what does the reaction do? It shifts away from that, and so it will shift to the left. Now this is important. Changing the temperature does change the equilibrium constant. Can anybody tell me why? Or tell me why it doesn't change the equilibrium constant when we're dealing, like if we were adding NH3, that wouldn't change the equilibrium constant, but adding heat does. Heat is not a term in the equilibrium expression. See, if we're just dealing with concentrations of these guys, and we add some of this, and then that goes back down, and these go up, and they're going to go to the same K. But now by adding heat, we're decreasing this and increasing those, the equilibrium constant will change. So if you have an exothermic or an endothermic reaction at a different temperature, the equilibrium constant will be different. If we lower the temperature of an exothermic reaction, that's like removing a product. It will shift to the right, trying to replace it. So it's a very shifty discussion. And that's going to make K larger, because this will also increase, and these will decrease. And so K gets bigger for an exothermic reaction when you lower the temperature. It favors the products, and it favors the reactants, smaller K, if you raise the temperature. It's the opposite with an endothermic reaction. For me, there are just way too many things here to just remember them, right? We get the big concept of Le Chatelier's principle, and then we just think about it. So, this is a cool reaction. So N2O4 is a colorless gas, and NO2 has a brown color to it. And this equilibrium, as written here, is an endothermic reaction. So here we've got a tube that's sealed, and it has a reaction mixture in it. So here we lower the temperature. I don't know if we got dry ice in there. What's that temperature say? I think it says negative 75. That's pretty cold. You gotta have dry ice in there. The color of the tube tells us that the reactant is favored, because we've removed heat. We've made it cold, and so the reaction shifts to the left. Here we warm it up. I didn't want to do that. Good grief. Come on, 26.2. So this is room temperature, and the tube turns brown. We've added heat. Adding heat causes the equilibrium to shift to the right. And you can go back and forth, brown and clear, all day long. It's just the temperature. Yeah, it does look like fun, doesn't it? If it was not an endothermic exothermic reaction, it's exothermic one way, endothermic the other, right? If energy was not part of the equation, changing the temperature wouldn't affect it at all, because it would not shift. So here's a summary of exothermic and endothermic and what increasing the temperature does. So the following reaction is exothermic. So what I want to do to that then is I want to put heat in as a reactant or product. For an exothermic, do I put it as a reactant or a product? It's a product. It's giving off heat. What's the effect of increasing the temperature? That's adding product. It'll shift to the left. How about decreasing? It'll go the other way, shift to the right. Any questions?